Good day everyone, my name is Pei Wei and we have Kenji, Ziqi, Nicholas and Tong. Our project is about DC motor speed control for electric fan applications. DC motors are commonly used in modern fans because they are energy efficient, quiet and easy to control. However, conventional DC motor systems often suffer from poor speed regulation, especially when there are disturbances such as aerodynamic drag, friction, or voltage fluctuation. Without a proper feedback controller, the motor speed may become unstable, sluggish, or unable to maintain the desired rotational speed under varying load conditions. Therefore, a closed-loop control system is required to ensure stable, smooth, and accurate speed control performance. In this project, MATLAB and Simulink are used to model, analyze, and improve the DC motor system. The objectives of this project are divided into three main parts. First, to mathematically model the DC motor system and derive its transfer function. Second, to analyze performance of the uncompensated system, including the response, steady-state error, and stability characteristic. Lastly, to design a suitable controller to improve the overall system performance by reducing overshoot, reduce settling time, improving stability, and minimizing steady-state error.
DC motor is considered as an electromechanical system because it will convert electrical voltage into mechanical rotational energy. The DC motor is separated into two parts, which are the electrical domain and the mechanical domain. The equation used in the electrical domain is derived using the Kirchhoff's voltage law. The input voltage is equals to the armature resistance times the armature current plus the armature inductance multiplied with the rate of change of current plus the back EMF. The back EMF is proportional to the rotational speed of the rotor, and the constant is the back EMF constant. Substituting the back EMF into the first equation and perform Laplace transform, we'll get the equation at the bottom left. For the mechanical domain, the equation is derived using the Newton's second law. The torque produced by the motor is proportional to the armature current, and the constant refers to the motor torque constant. The torque is equals to the mass moment inertia multiplied with the angular acceleration plus damping multiplied with the angular velocity plus the load torque. Substituting the first equation into the second equation and perform Laplace transform, we will get the equation at the bottom right. Using the two equations we derived in the previous slide, we can substitute the second equation into the first equation to get the transfer function of the DC motor. The first diagram shows the block diagram of the DC motor, and it can be simplified into a single block which represents the transfer function of the DC motor. From the block diagram, we can see that the back EMF is generated by the rotation of the rotor, which opposes the input voltage, and there is a load torque which acts as a disturbance to oppose the torque generated by the motor. The diagram shows the closed-loop unity feedback systems when the DC motor is installed in a control system. There are two types of inputs, which are the desired angular speed and the load torque, which is the disturbance. The output speed will be sent to the controller, and the controller will compare the difference between the output and the desired speed. It will generate a voltage and send to the DC motor to adjust the output speed so that the output speed is equals to the inputs. The equation for closed-loop transfer function without the controller is equals to the plant transfer function divided by 1 plus the feedback multiplied with the plant transfer function.
To see how this DC motor behaves before we add any external fixes, we ran a time response analysis on the uncompensated system. When we plug in our motor constants, the system is identified as second order underdamped system. And from the comparison table, our manual calculations perfectly match our experimental MATLAB simulation. But the big problem is that we have an overshoot of 29.3%. If you look at the step response graph on the right, the angular velocity spikes way past its target before settling down. And in real-world application, this sudden speed surge creates massive mechanical wear and tear on the motor. Furthermore, because it's a Type 0 system, it suffers from huge steady-state tracking error of 0.412 rads per second. This means that if you don't command the motor to run at 1 rad per second, it can only manage to reach 0.588 rads per second. So our baseline test proves that the uncontrolled motor is highly oscillatory and inaccurate. So this sets up our primary objective, where we need to design a controller that can reduce this overshoot and bring our tracking error down to 0.
So what is steady-state error? Steady-state error measures how accurately the motor can achieve the desired speed after all transient effects have disappeared. In this analysis, the uncompensated DC motor is evaluated under both reference and disturbance step inputs. Using the final value theorem, the position error constant was found to be 1.428. The steady-state error consists of contributions from both the reference input and the disturbance input, resulting in a total error of 1.588 radian per second. The MATLAB simulation closely matches the theoretical calculations, validating the derived equations. The motor only reaches approximately 0.588 radian per second instead of the desired 1 radian per second. This confirms that the uncompensated Type 0 system has insufficient tracking performance and requires controller design for accurate speed tracking.
Moving to slide 3.3, let's discuss the stability of the system. Our first critical takeaway is that the system exhibits absolute stability, which we have rigorously verified using the board plot. Looking at the hole placement, our analysis shows that the closed loop holes lie strictly within the left half plane. This is vital because it ensures the system's output will never explode or grow infinitely. Instead, it remains bounded and predictable. One fascinating characteristic revealed by the board plot is the gain margin, or rather the lack of a finite one. In this specific configuration, the system gain can be cranked up indefinitely without triggering instability, providing us with a highly robust system in terms of gain. However, we must respect the physical constraints. We have a strict delay margin of 0.0387 seconds. What this means for our hardware implementation is that if the controller lag exceeds this 38 millisecond threshold, the phase lag will push the system past the stability point and it will break. In summary, the system is robust in gain but exceptionally sensitive to timing.
Good day everyone, I'm Nicholas. Let's talk about the design of the control system. The main objectives of this controller design are to improve the transition response, decrease the steady state error, minimize the percentage overshoot, and maintain a setting time below 0.5 seconds. To achieve these objectives, two controllers were investigated, namely the proportional integral PI controller and the proportional integral derivative PID controller. First, a PI controller was designed. The purpose of introducing the PI controller was to eliminate the steady state error, improve speed regulation, and convert the system from Type 0 to Type 1. The controller parameters were determined through tuning, and the selected values were Kp equal to 3 and Ki equal to 25. During the design process, a higher proportional gain was used to increase the response speed. However, excessive Kp can result in higher overshoot and oscillatory behavior. The integral gain was introduced to eliminate the steady state error. On your left-hand side, you can see the block diagram of PI-controlled DC motor system, and on the right is the reduced block diagram of PI-controlled DC motor system. At the bottom is a simulation of PI-controlled DC motor system in Simulink of the MATLAB. On the left is the closed-loop step response graph of PI-controlled DC motor system. On the right is the result obtained from the graph by using MATLAB coding system. Below is the comparison of time response result without and with PI controller. Based on the result, the rise time improved from 0.0342 seconds to 0.0233 seconds, and the steady state error was successfully reduced from 0.412 radian per second to 0. However, the overshoot increased from 29.29% to 34.27%, and the setting time also increased to 0.3466 seconds. Although the PI controller eliminated the steady state error, further improvement was required in setting time and also to reduce the overshoot. To overcome this limitation, a PID controller was implemented by adding derivative action. The derivative gain was introduced to reduce overshoot, improve damping, and enhance the transition response of the system, while the excessive KD will cause the slower response and increase the setting time. Thus, three values of KD were investigated, which were 0.005, 0.05, and 0.5. On the left is the block diagram of PID controlled DC motor system, while on the right is the reduced block diagram. At the below is the simulation of PID controls DC motor system in Simulink that done in the MATLAB. On the left is the closed-loop step response graph with KD equal to 0.05, while on the right is the comparison of time response result with different KD values. After comparing the time response result, KD equal to 0.05 was selected because it provided the best overall performance. It achieved the lowest overshoot of only 0.1246%, while maintaining a setting time of 0.2883 seconds and zero steady state error. Finally, the performance of the PI and PID controller was compared on the table at the below. The PID controller significantly reduced the overshoot from 34.27% to 0.1246% and reduced the setting time from 0.3466 seconds to 0.2883 seconds, while maintaining zero steady state error. Therefore, the final PID controller with Kp equal to 3, Ki equal to 25, and Kd equal to 0.05 was selected. The PID controller satisfied all design objectives while providing improved transition response, zero steady state error, the lowest overshoot, and a setting time below 0.5 seconds.
To conclude, the uncompensated DC motor system was found to have several limitations. Although the system was stable, it exhibited a noticeable steady-state error and poor disturbance rejection capability, meaning that it could not accurately maintain the desired speed when external loads were present. To address these issues, a PID controller was designed and tuned with parameters Kp equals to 3, Ki equals to 25, and Kd equals to 0.05. The integral action successfully eliminated the steady-state error, while the derivative action improved damping and reduced oscillations. As a result, the compensator system achieved a rise time of 0.0268 seconds, a settling time of 0.2883 seconds, and an overshoot of only 0.1246%, while maintaining zero steady-state error. These results satisfy all the design objectives established at the beginning of the project. Furthermore, the analytical calculations, MATLAB analysis, and Simulink simulations showed strong agreement, validating the entire control system design process from mathematical modeling to controller implementation. Overall, the PID-controlled DC motor provides accurate, stable, and responsive speed control, demonstrating the effectiveness of the proposed control strategy. Thank you.